Today we'll talk about planning. Recall that we had said that an intelligent agent maps perceptual histories into actions. Planning is a powerful method for action selection. We'll use the syntax we learned from logic last week to set up the specification of goals and states and operators for moving between states and achieving goals. We'll see that when there are multiple goals, there can be conflicts between them. We'll describe a specific technique called partial order planning that avoids conflicts between multiple goals. Finally, we'll talk about a representation called hierarchical task networks that allows us to make complex hierarchical plans. In order to look at planning in detail, let us consider this problem that we have encountered earlier. This is a blocks world in which there is a robot which has to move the blocks from the current state to the goal state. The robot has only one arm, so it can move only one block at a time. It can move only a block which does not have some other block on top of it. Earlier, when we considered this method, we had looked at weak AI methods like mean sense analysis. Now we're going to look at more systematic, knowledge-based methods. One question unanswered in our previous discussion was, how can we find which goal to select among the various goals that are here? We simply said the agent might select a goal. Now we will look at how the agent can in fact do the goal decomposition and select the right goal to pursue. Let us consider a little bit more realistic problem. Imagine that you were to hire a robot, and the task of the robot was to paint the ceiling in your room and also paint the ladder. So two goals here, paint the ladder, paint the ceiling, and note that the two goals are in conflict. Because if the robot paints the ladder first, then the ladder will become wet, and then the robot cannot climb on it in order to paint the ceiling. So the robot must really first paint the ceiling, then climb down, then paint the ladder, and everything is okay. You would expect a human to get this almost immediately. You probably got it almost immediately. You have to paint the ceiling first before you paint the ladder. Of course, every time I have hired construction workers, they always paint the ladder first, then they go and take a break, and so that I have to pay them anyway. We will accept that kind of behavior from human construction workers. We would not accept that from robot construction workers. The robots must be intelligent and must know how to prioritize the goals. Well, in order to reason about these goals, the robot first must be able to represent them. So how can we represent the goal of painted ceiling? Now that we have learned about proposition logic, here is the proposition that can represent painted ceiling. This is the object, this is the predicate on it. So in this box, please write down the second goal of painting the ladder in propositional form. And having done that, in this box, write down how would we represent the two goals as a conjunction. David, what do you think?
So the second goal is pretty straightforward. We're using the same proposition, but here we're operating on the ladder instead of on the ceiling. And then for the goal state, we're just going to link the two together with a conjunction. So we're saying that our goal state is painted ceiling and painted ladder.
Good. Let's move on then. So we just talked about goals and the goal state of the goals. In order to specify the goal fully, we need to not only specify the goal state, but also to specify the initial state. So let's do that. Let us suppose that the initial state in this world is that the robot is on the floor. Note how I'm writing this. On is a predicate. This is a two-tuple, and I'm reading this as robot on floor. So the robot on floor, and the ladder is dry, and the ceiling is dry. So this is the initial state. This is the goal state. Now we have fully specified the goal. Let's now ask, how can the robot come up with a plan? Now that we have learned how to specify the initial state of the world and the goal state of the world, let us do an exercise in specifying other states of the world. So please write down in this box the state of the world that would occur after the robot is on the ladder and the ceiling has been painted. How did you specify the state, David?
So earlier when we were talking about our goal state, we had specified that we wanted our ceiling to be painted, and we wrote that as painted ceiling. So if in this state the ceiling is painted, I'll write that as painted ceiling. Earlier in the initial state, we said that the robot was on the floor, and now we know that the robot is on the ladder. So I'm going to say robot on ladder. And this is an and, so I'm going to join them with a conjunction right there. I wasn't given any other information about the world, so I'm not including anything else in this state.
That's good, David. In general, if there is information about the initial state, additional information, for example, dry ladder and dry ceiling, then those assertions about the world can be propagated to the subsequent states, provided that no operator in the middle in the middle of this initial state and this state actually negates or deletes any of these assertions. We'll see more of this in just a minute. Now that we have learned how to specify states in planning, let us look at how to specify the operators. So consider the operator climb ladder. We might specify the climb ladder operator and any other operator in general through a set of preconditions and postconditions. So for the climb ladder operator, the precondition might be that the robot is on the floor and the ladder is dry. Notice that these are being written in the language of propositional logic. And the postcondition for the climb ladder operator might be that the robot is on the ladder. This captures the notion that the robot has climbed the ladder. It was earlier on the floor and later on it's on the ladder. Several things to note here. First, by convention, the precondition does not have any negative literals. All the literals in the precondition are positive. Postconditions of operators may have negative literals. Second, the meaning of these preconditions and postconditions is that these assertions are true in the world before this operator can be applied, and that these assertions become true in the world after this operator has been applied. This captures the syntax of the operator climb ladder. The semantics of this operator is that this operator can be applied if and only if the preconditions of the operator are true in the world. It cannot be applied if the preconditions are not true in the world. Now that we have learned how to specify an operator such as climb ladder, let us do some exercises about how to specify other operators like descend ladder, paint ceiling, and paint ladder. In these boxes, please write down the preconditions and the postconditions in the same notation. David, what did you come up with?
So the descend ladder operator is pretty similar to the climb ladder operator. We still have to have a dry ladder in order to climb up or down the ladder. This time, in order to climb down the ladder, we have to already be on the ladder. So our preconditions are that we're on the ladder and the ladder is dry. Our postcondition is that we're now on the floor, so we just kind of flipped the climb ladder operator. For paint ceiling, we know that the robot has to already be on the ladder in order to reach the ceiling, so the precondition here is that the robot is on the ladder. After it's painted the ceiling, we have two things. The ceiling is now painted, and the ladder is not dry. We haven't seen this before, but this goes back to what you were saying, Ashok, about we have to explicitly negate things that were true in the world before. The ceiling was dry, but now it's not dry. Similarly, for painting the ladder, the robot has to be on the floor. It can't paint the ladder while it's standing on it. And the postcondition is that the ladder is painted and that the ladder is not dry.
This is right, David. Let us note a couple of other things. First, note how propositional logic is providing precision to the specification of these operators. That's the power of logic. It provides clarity and precision. The other is, once again, note that the preconditions have only positive literals, while the postconditions may have negative literals as well.
So Ashok, why is it that we can't have negative literals in our precondition? Why can't we just say not painted ladder instead of dry ladder?
David, this has to do something with the history of these notations. This notation comes from STRIPS, a planner developed in the late 60s at the Stanford Research Institute, one of the early robot planners that ran on a robot called Shaky. STRIPS, the planner, used theorem proving to form plans, and it turned out that the use of only positive literals in the preconditions made the theorem proving processes more efficient. This convention has just stayed in AI since the time of STRIPS and Shaky. Before we go further with planning, let us see how planning differs from search and from other methods like mean-sense analysis that we have come across earlier. In fact, some of you may recognize this particular figure. We had exactly the same figure when we were talking about mean-sense analysis. Well, first let us compare planning to search. Here is what we could do. Given the initial state, we could apply to the initial state all the operators that are applicable to the initial state. That will give us a range of states. Then to each successor state, we could apply all the operators that were available to that state. That will give us more states. And so we could keep on expanding this. But I'm sure you can see what will happen. There will be a combinatorial explosion in this. Search for this problem is extremely inefficient.
So to take an example of this, this would be like if you were trying to plan a route somewhere, and at each individual intersection, you took each possible turn as a different possible operator to get to the next state. Then for every intersection that those turns led to, you'd consider each turn at those intersections, even if they were taking you far away from your actual goal destination. You can imagine that if you were to look at every single intersection that you encounter on your drive, and every single possible intersection that follows from those turns, you'd get an enormous number of possibilities very quickly, the vast majority of which you're not actually interested in.
That's good, David. And to build on this example, what do we actually do when we have to plan a navigation route to go from one location to another location in an urban area? We use knowledge of the goal. The goal tells us what turn to take at every intersection. We want to take a turn that helps us get closer to the goal. So one thing we are learning here is that there are different kinds of knowledge. There is knowledge about the world, the intersections and the turns, the states and the operators more generally. There is also tacit knowledge about how to do the operator selection, how to select between various turns at any intersection. This knowledge is tacit and is sometimes called control knowledge. Goals provide us with the control knowledge of deciding how to select between different operators. Let us recall how mean-sense analysis worked. How goals provided control knowledge in mean-sense analysis. Mean-sense analysis is a heuristic method in which we would compare the current state and the goal state and enumerate the differences between them. Then we'll select the operator that will help us reduce the largest difference between the current state and the goal state. That's one way of using goals as control knowledge to select between operators. Planning provides more systematic methods for selecting between different operators. So the real problem now becomes how to do operator selection, which is the same problem as how to do action selection. Recall that when we were talking about intelligent agents, we defined intelligent agents as agents that map perceptual history into actions. Action selection was a key problem, was a central problem. This is why planning is central, because it deals directly with action selection or with operator selection. Operators are simply mental representations of actions available in the world. So let us look at what a plan might look like in the language that we have been developing for planning. A plan might look like this. Here is the initial state and a set of successor states. A series of states punctuated by the operators that transform one state into another. Here we have expanded this operator paint ceiling on the right to specify its preconditions and postconditions, and there are several things noteworthy here. Note that the preconditions of this operator exactly match the predecessor state. So we have on-robot ladder here, and we have on-robot ladder here. So some assertions of the world are true here, and those assertions match the precondition, which is why this operator is applicable. Similarly, the postconditions of this operator directly match the assertions about the world in the successor state. So I have painted ceiling here, there is painted ceiling there. There is not dry ceiling here, there is not dry ceiling here. So this provides a very precise way of specifying the states and the operators and the exact connections between them. Let us return to mean-sense analysis for just another minute, just to see how mean-sense analysis might try to work for this problem and get into difficulties. So this is the goal state, painted ladder and painted ceiling, and this is the initial state. Now, mean-sense analysis may enumerate the operators that are applicable to painted ladder and to painted ceiling. Here the operator might be paint ladder. Here the operator might be paint ceiling, but that requires some precondition climb up ladder, which does not satisfy the initial state. So mean-sense analysis may pick the goal painted ladder and select the operator paint ladder, which gets the mean-sense analysis to this state. This is the heuristic method. Here is the paint ladder specified at the right, and you can see the preconditions of paint ladder match the initial state and the postconditions match the successor state. Now that mean-sense analysis has achieved the first goal of painted ladder, it may turn to the second goal of painted ceiling. Recall that this is the current state. So mean-sense analysis may pick the operator climb ladder as a precondition for the operator of painted ceiling. But note what happens. The precondition of climb ladder conflicts with the postcondition of paint ladder. This was not dry ladder. This requires dry ladder. There is a conflict here. In a situation like this now, the robot would need to just wait for the ladder to become dry again before climb ladder is applicable. So it seems as if the people that I sometimes hire for working on my home are using mean-sense analysis. They first paint the ladder, then they go wait until the ladder dries up, and then they of course expect me to pay them for their time. To summarize, we have a plan for achieving one of the goals, painted ladder. But this particular plan clobbers achieving the other goal, painted ceiling, because it creates a condition that makes it impossible to achieve the other goal. So the question now becomes, how may an intelligent agent actually reason about the conflicts between these goals? How can planning systematically find out how to organize these various operators so that these conflicts do not occur? What we have described here, this goal clobbering, is true for all simple planners, sometimes called linear planners. A linear planner does not try to reason about the conflict between these goals, does not try to reason about how the plan for one goal may clobber another goal. Instead, it just goes about making plans as if these goals can be achieved in any order. This introduces us to the need for partial order planning. Partial order planning occurs when there are multiple goals, and the plan for achieving one goal clobbers another goal. David, can you think of an example of partial order planning?
So actually, I do have a kind of funny example of partial order planning. Not long ago, we bought a couch, and to keep things simple, we decided to pay them to assemble the couch for us. Then we got the couch home and found out that once the couch was already assembled, it would not fit through the apartment door. So we had to completely disassemble the couch, move the pieces in one by one, and then reassemble the couch. So the plan for assembling the couch clobbered the goal of getting the couch into the apartment.
Good example. Now, next we'll discuss how partial order planning can help us detect conflicts like this and avoid them. Now let us see how partial order planning, sometimes also called nonlinear planning, may work for our ladder and ceiling problem. So here is a goal state, painted ladder. Here is the initial state. We can now use the goal knowledge as control knowledge to select between different operators available in this world. The only operator whose post conditions match the goal condition of painted ladder and whose preconditions are compatible with the initial state is paint ladder. So we'll select that operator. When we think of applying the operator paint ladder to the initial state, we get this as the successor state. Painted ladder and not dry ladder are coming from the post conditions of paint ladder. Robot on floor and ceiling dry are being propagated from the initial state. We changed dry ladder to not dry ladder because that was the post condition of paint ladder. We did not change the on robot floor and dry ceiling because paint ladder was silent about them. Now that we have seen how a simple planner may work for this goal, let us see how the simple planner, the linear planner, may work for the goal of painted ceiling. Please write down the operators in these boxes and the states that will be achieved after the application of these boxes in these bigger boxes. What did you write, David?
So I can tell that the first thing the robot is going to have to do to paint the ceiling is climb the ladder. So I'm first going to apply the climb ladder operator. That's going to result in the robot being on the ladder, but the state of the ladder and the ceiling haven't changed. Then now that the robot is on the ladder, it'll apply the paint ceiling operator, which results in painted ceiling being added to the state and the dry ceiling being negated.
That's good, David. So this is the structure of the final plan. But another question to ask here is, how might the robot come up with such a plan? So let's do the same thing that we had done here earlier. We're going to use goal as a control knowledge to select an operator. So we know that we want to have the ceiling painted. So the question then becomes, of the available operators, which operator has a post condition painted ceiling? And the only operator whose post condition is painted ceiling is the operator paint ceiling. So we select that operator. So we're working backwards here. Painted ceiling was our goal condition. We selected paint ceiling as the operator. But this paint ceiling now has some preconditions. One of the preconditions is on robot ladder, which is different from on robot floor in the initial state. So now the question becomes, how can we achieve the sub-goal of robot on ladder? If we use that sub-goal as the control knowledge, then we want to select an operator whose post conditions will match this sub-goal. And that operator is climb ladder. So now we apply climb ladder here, and the preconditions of climb ladder match this initial state. And that is how we get to this plan, climb ladder and paint ceiling. So we are working backwards using goal knowledge as control knowledge to select between operators.
So note that we just made a connection back to problem reduction that we talked about right after means ends analysis. Ashok in his description talked about the sub-goal of getting up the ladder. When we talked about problem reduction earlier, we talked about the need to break big problems down into smaller problems, but we didn't talk exactly about how an agent would go about doing that. Here we see one way in which an agent would go about actually identifying those sub-goals to accomplish in order to accomplish the final goal.
So what the partial order planner has done so far is to view the two goals as if they were independent of each other and come up with a partial plan for each of the two goals. It has not yet detected any conflicts between them, let alone resolve those conflicts. The next thing would be to examine the relationship between these two plans and see if there are any conflicts between them. But how might a partial order plan go about detecting conflicts between two plans? So here is plan 1, imagine, here is plan 2. The partial order planner may go about detecting conflicts by looking at each precondition in the current plan. And if the precondition of an operator in the current plan is clobbered by some state in the another plan, in the second plan, then the partial order planner will know there is a conflict between them. Then it can go about resolving these conflicts by promoting or demoting one plan's goal over another plan's goal. Thus, if some state in plan B clobbers the application of some operator in plan A, then we may want to order the goals in this plan and this plan in such a way that this operator is done before that state is achieved. Now let us see how the partial order planner may go about detecting conflicts between these two plans. So the partial order planner may begin with his plan for painting the ladder and see whether the precondition of this operator paint ladder are clobbered by any state in the second plan. As it turns out, that doesn't happen in this example. Now the partial order planner may look at the operators in the second plan and see whether the preconditions of any of the operators are clobbered by some state in this first plan. So let's look at climb ladder here. The precondition of climb ladder is on robot floor and dry ladder. And as this precondition is compared with the states in the first plan, we can immediately see the conflict. Here is dry ladder and here it is not dry ladder. And this way, the partial order planner has been able to find that one of the states here in the first plan clobbers the precondition of one operator in the second plan. To resolve this conflict, the partial order planner may promote these goals over the goal of painting the ladder. Some of you may also notice that after the robot has painted the ceiling, the robot is on ladder. But in order to apply the paint ladder operator, the robot must be on the floor. So here there is an open condition problem. This particular condition for this operator is not being satisfied when the robot is on the ladder. We'll come to this in a minute. So recall that in order to resolve the conflict, the partial order planner has decided to promote this goal over that one. As it tries to connect these two plans, it finds that there is an open condition problem that we just talked about. On robot ladder does not match on robot floor. So now it needs to select an operator whose postcondition will match this state, robot on floor, and whose preconditions will match this state, robot on ladder. And there is just one operator that matches those conditions. And that operator is descend ladder. So now the partial order planner uses this information to select the operator descend ladder, and now we have a complete plan. So now you know about the algorithm for partial order planning and how it works in practice. But what does this tell us about intelligence? Let's consider several postulates. First, knowledge is not just about the world. Knowledge is also controlled knowledge. That is often tacit, but this controlled knowledge helps us select between operators. Second, that goals provide control knowledge. Goals can be used to decide between different operators, and we select an operator that helps us move closer to the goal. Third, we can view partial order planning as an interaction between several different kinds of agents or abilities. Each agent here represents a small micro ability. There is this agent which was responsible for generating plans for each of the goals independently. Then there was an agent responsible for detecting conflicts between them. Then there was a third agent responsible for resolving these conflicts. So we can think of partial order planning as emerging out of interaction between three different agents, each one of which is capable of only a small ability. So we can think of partial order planning as emerging out of interaction between three agents, where each agent is capable of only one small task. Minsky has proposed the notion of a society of mind, a society of agents inside an intelligent agent's mind that work together to produce complex behavior, where each agent itself is very simple. As in this case, a simple agent for detecting conflicts, a simple agent for resolving conflicts, and of course an agent for making simple plans for simple goals. There is one other lesson to take away from here. When you and I solve problems like the ladder and the ceiling problem, we seem to address these problems almost effortlessly and almost instantaneously. So it looks really simple. What AI does, however, is to make the process explicit. To write a computer program that can solve the same problem is very hard. It is hard because the computer program must specify each operator, each precondition, each state, each goal, every step very, very clearly and very, very precisely. By writing these computer programs, these AI agents that can solve this problem, we make the process that humans might be using more explicit. We generate hypotheses about how humans might be doing it, which is a very powerful idea. Now that we have seen partial order planning in action, let us try to do a series of exercises to make sure that we understand it clearly. We have come across this problem earlier. This is the micro-world of blocks. Here is the initial state, and here is the goal state. We need to transform this initial state to the goal state, moving only one block at a time. Please write down the initial state and the goal state in propositional logic. What did you get, David?
So our initial state is that each block is on top of the other. D is on B, B is on A is on C, and C is on the table. Our goal state is each block on top of the other in a different order, in alphabetical order. So A is on B is on C, and C is on the table. So our initial state is that the blocks are all stacked up. D is on B is on A is on C is on the table. And our goal state is that the blocks are stacked up in alphabetical order. So A is on B is on C is on D, and D is on the table.
Know that we humans find addressing problems like this almost trivial. We know what to do here. Put D on the table, put B on the table, and so on, and then put C on top of D, and so on. The question is, how can we write an AI program that can do it? And by writing an AI program, how can we make things so precise that it will provide insight into human intelligence? To do this, let us start writing the operators that are available in this particular world. There are really two operators. I can either move block X to block Y, which is the first operator here, or I can move blocks X to the table. Note two things. First, instead of saying block A and block B, we have variabilized them, move block X to block Y, where X could be A, B, C, or D, and similarly for block Y. And this is just a more concise notation. Second, that in order to move block X to block Y, both X and Y must be clear. That is, neither X nor Y should have any other block on top of them. Given this setup, please write down the specification of the first operator as well as the second operator. What did you write down, David?
So like you said, our precondition for the first one is that both X and Y are clear. We can't move X if anything's on top of X, and we can't put it on Y if something is already on top of Y. Our postcondition then is that X is on Y. For the table, it's a little bit easier. The table has unlimited room. So for the table, as long as X is clear, we can move X to the table. And then the postcondition is that X is now on the table.
So given the various goals here, A on B, B on C, and so forth, write down the plan for accomplishing each goal as if these goals were independent of each other. We have shown here only 3 goals here, not the fourth goal of D on table because of lack of space, but D on table anyway is trivial. So David, what plans did you come up with?
So like you said, Ashok, the plan of putting D on the table is kind of trivial, and we actually see that it's the first step of any other plan, so we don't really need to articulate that explicitly. For putting A on B, our fastest idea would be to put D on the table, then to put B on the table, and to put A on top of B. That would just get us straight to putting A on B. For putting B on C, we need to put D on the table, B on the table, A on the table, and then move B onto the top of C. And then for putting C on D, we would need to move D to the table, B to the table, A to the table, and then put C on top of D.
Now that we have these 3 plans for accomplishing the 3 goals, can you detect the conflicts between these plans? Use a pencil and a piece of paper to detect the conflicts and resolve the conflicts, and then write down the ordering of the goals in these boxes. What ordering did you come up with, David?
So what we see is that each goal actually clobbers the next goal in its last step. So the postcondition of move A, B is that A is now on B. But a precondition for move B, C is that B is clear. Because A is on B, B is no longer clear, so we can't move B to C. So this plan has clobbered this plan. Similarly, if we move B to C, we no longer can move C on top of D because C is no longer clear. So this plan has clobbered this plan. So we're going to need to do this plan first, then this plan, then this plan.
Good, David. Now that we know about the conflicts between these plans, please write down the final plan for achieving the goal state. To save space, just write down the operators. You don't have to specify all the states in this plan. David, what plan did you come up with?
So the first thing we did was we executed the plan for moving C onto D, which was to move D, B, and A all onto the table, and then to move C onto D. Then having done that, we looked at the next goal, and we found out that most of the steps in the plan for moving B on C were actually accomplished in the process of moving C on D. So we can actually go ahead and put B on C here. Then we looked at the goal of having A on B and found that all the steps for moving A onto B had already been accomplished, so we just put A onto B directly.
That's good, David. Note that when we did this problem previously using mean sense analysis and problem reduction, we ran into all kinds of problems because plans were clobbering goals and we had no way of ordering these various goals. Now we have a way. That's the power of partial order planning. Note also that this partial order planning, this AI algorithm, makes certain things that are implicit in human reasoning explicit. Presumably, when you and I reason about these things, we must be reasoning something like this, or at least this is one hypothesis about how we might be reasoning, and we have just made many of the operations of human reasoning so explicit and so precise. Our next topic in planning is called hierarchical planning. We'll introduce the idea to you. We'll also introduce a representation called hierarchical task network to you. HTN for hierarchical task network. To illustrate hierarchical planning, imagine that we are still in the blocks micro world. Here is the initial state and here is the goal state. These states are more complicated than the initial state and goal state we have encountered so far. So as previously, we can use partial order planning to come up with a plan to go from this initial state to goal state. Here is a final plan, and as you can see, it's pretty long and complicated with a large number of operations in them. So the question then becomes, can we abstract some of these operations at a higher level so that instead of thinking in terms of these low-level move operations, we can think in terms of higher-level macro operations, and those macro operations will then make the problem space much smaller, much simpler, so that we can navigate it, and then we can expand those macro operators into the move operations. So look at the macro operators at a high-level abstraction. Consider just one part of the current problem. Here is the initial state, here is the goal state, here is a final plan. To illustrate this idea of macro operators and hierarchical planning at multiple levels of abstraction, let us revisit this problem that we had encountered earlier. This was the initial state, this was the goal state, and we came up with this as the final plan. Now we can think of these three operations as being abstracted out into a macro operator that we can call unstack. And these three operations being abstracted out into a macro operator that we can call stack ascending, which is simply saying stacking them in a particular ascending order. Here is the specification of the two macro operators, unstack and stack ascending. You have the preconditions and the postconditions, and this macro operator also tells you how this macro operator can be expanded into the lower level move operations. Similarly for the stack ascending macro operator. Now that we have illustrated hierarchical planning, what does it tell us about intelligence? Intelligent agents, both cognitive and artificial, constantly faced with large, complex problems. The problem spaces corresponding to these problems often have combinatorial explosion of states in them. Intelligent agents address these complex problems by thinking at multiple levels of abstraction, so that at any one level of abstraction, the problem appears small and simple. In order to be able to reason at this multiple levels of abstraction, we need knowledge at multiple levels of abstraction. In this case, there was knowledge not only at the level of move operations, but also the level of macro operations like unstack and stack ascending, and perhaps even high-level macro operations like sort. This goes back to the fundamental notion of knowledge-based AI. Intelligent agents use knowledge in order to be able to tackle hard, complex problems.
How would you use planning to develop an agent that can answer Raven's progressive matrices? So the first question you'll want to ask here is, what are our states? What's our initial state? And what's our final state? Given that, what are the operators that allow us to transition between them? How would we select those operators? We talked about partial order planning in this lesson. What conflicts are possible when we're trying to solve Raven's problems? How do we detect those conflicts beforehand and avoid them? Note that again, we can consider this at two different levels. First, we can think of the agent as having a plan for how to address any new problem that comes in. Or second, we can consider the agent as discerning the underlying plan behind a new problem. So today we've discussed how to plan out actions using formal logic. We started off by talking about states, operators, and goals in formal logic. We then used those to contextualize our discussion on detecting conflicts that might arise. This introduced the need for partial order planning, which helps us avoid those conflicts beforehand. Finally, we talked about hierarchical task networks, which can be used for hierarchical planning. Now we're going to move on to understanding, which builds on our notion of frames from a few lessons ago. But if you're interested in this, you can jump forward to our lessons on design, configuration, and diagnosis, leverage some of the concepts of planning very heavily.
Planning is another process central to cognition. It is central because action selection is central to cognition. You and I are constantly faced with the problem of selecting actions. Where should I go for dinner today? What should I cook for dinner today? How do I cook what I wanted to cook? I got a bonus. What should I do with the bonus? Should I go for a vacation? How should I go to a vacation? Where should I go to a vacation? These are all problems of action selection, and I need planning to select the appropriate actions. Cognitive agents also have multiple goals. As a professor, one of my goals right now is to talk with you. Another goal that I have is to become rich, although I know that becoming a professor is not going to make me rich. The point is that cognitive agents have multiple goals that can have interactions between them. Sometimes the interaction is positive. Achieving one goal provides an opportunity for achieving the second goal. Sometimes the interaction is negative. There are conflicts. Cognitive agents detect those conflicts. They avoid those conflicts. And planning then is a central process for achieving multiple goals at the same time. Please write down what you learned in this lesson.
Great. Thank you so much for your feedback.